Hello everyone. Today's video is hopefully going to supplement some of the things that we've already worked with in terms of our new unit of Chapter 9 in vectors. We've already gotten through some of the basics of the notation of vectors, some of the language of vectors. We then moved to kind of the geometry of vectors, understanding them as kind of that directed line segment that can be used to help us model certain types of movement. It can be even used to prove a lot of the things that we already maybe can prove using geometry methods. We then move to some of the more algebraic representations of vectors. We used words like component form, position vector, and again we were able to solve some problems using vectors that through our geometry methods might be a little bit awkward or long. And sometimes they're the same, but it's just another nice method. The next step is to start working with other operations of vectors, and the first of those is something called the scalar product. Now what I have up here is a definition of a scalar product. It's as simple as that. It's defined. And what we have is if we're given two vectors, A1, A2, B1, B2, the scalar product, or sometimes called the dot product, because we use a big dot to represent it, is going to be kind of the sum of those products, A1, B1 plus A2, B2. And by the way, the real power of this is when we get into 3 dimensions. Because when we move into 3 dimensions, if we have an A3 and a B3, we just tack on the next product, A3, B3. Now, what does this scalar product tell us? Well, before we get into that, there are some properties that I think you should read in the text. But one important property is the fact that any vector kind of composed with itself in terms of the scalar product is going to be the magnitude squared. And we could show that rather easily. Because if both of these were A1 and both of these were A2, it would be A1 squared and A2 squared. The magnitude is the square root of A1 squared plus A2 squared. So if you square it, you're back to an equation. So there are some of these problems that ask you to kind of manipulate some of these properties. Now, the real big thing between this, or the big thing so far, is we can use this scalar product to find the angle between vectors. Up to this point, you might have been able to use this scalar product just to determine if 2 vectors are perpendicular, and that's still used. But if 2 vectors are perpendicular, what that means is the angle between them is pi over 2 or 90. And of course, the cosine of 90 is 0. So the only way that this fraction can be 0 is if this scalar product is 0. So we know if the scalar product is 0, the lines, the vectors, whatever you're working with, are going to be perpendicular or orthogonal. Now, of course, this is more of a standard multiplication here. It's not a dot product because these aren't vectors. So context is important in understanding kind of the different types of multiplication. Once we get past that, what I'd like to do is give some examples that aren't in the mainstream. It's not just here are 2 vectors, find the angle between them. We have to maybe come up with the vectors on our own. So this first one is to find the angle between 2 lines. Now we can do this a variety of ways. You could graph it, you could make a triangle, you could use sine rule or cosine rule, you can use tangent, you can use a variety of things. There are some very quick ways, if you do a bunch of these in a row, that you can get the answer. But what we're going to try to do is live in the vector world with these lines. Well, in 2 dimensions, in the vector world, the direction of a line is just its slope. So if we think about this first one, we can see that the slope is -3. So if the slope is -3, that just means wherever this thing happens to be, if we go down 3, we'd go back 1. All right? So that would be a slope. And that's not going to be negative. It would be over here. Right? So if we think about that as a vector, if we use the x's first, it's going to be the vector 1. If we go forward, -3. Now I could say -1 and +3 would be the same type of thing. But that's going to be the value of that vector that represents that direction. This one, we have the slope of 2. So we can think of this as 1, 2. So if these are my two vectors, we can very easily now see the angle between them. So I can simply find the cosine of theta to be the dot product, which is going to be 1 times 1 plus -3 times 2 all over the magnitude of this one, which is going to be the square root of 10, times the magnitude of this one, which is the square root of 5. Doing a little bit more calculation, we have this to be 1 minus 6 and of course we can play with that a little bit. And then I'm not going to do the rest of it, but we can go ahead and find the angle based on what you know already. Now, one thing about two lines is, of course, when they cross, the angle between them could be kind of different depending on which one you might choose. These two are the same, these two are the same. So we typically like to get the acute angle between two lines, but it's not required. So if this happens to give you an obtuse angle, you'd probably take its supplement. So you would find the acute angle. The other way to look at it is whether or not this thing is positive or negative, but I'll let you kind of discover that and work with that. But the angle between two vectors could be found using this formula. And by the way, if we go back to this formula, this gives us another way to define, or not so much to define, but describe the dot product. We can actually call the dot product to be the product of the magnitudes times the cosine of the angle in between them, because that would just be changing that algebraically. So next, here we have a box. So the base is a square, everything rectangles, top's a square, and what we want to do is find the angle ABC. Measure of angle ABC. Now angle ABC would be, of course, kind of this angle that cuts through kind of this figure. That's kind of unfortunate the way I've drawn it, but we're looking at this angle down in here. Okay? But again, it's back into that function. You wouldn't see it, so that's a little better. All right? So we're looking for that angle. Well, your geometry brain might just start finding different sides, and again, try to use the law of sines, law of cosines, and that could definitely be possible, but I'm going to try to live in the vector world and see what vectors would do for us. The first thing I'll do is try to figure out this BA as a vector, and then I'll try to figure out BC. Well, I can talk about it in a variety of ways, but I just need to be consistent. For example, I'm going to call BA to be this direction, which is 2, then over, which is 4, and then down, which is 3. Again, I could have flipped these around a little bit, but then I'd have to be consistent over here. For BC, again, I'm going to go out, but in this case, I'm only going halfway, so that's just going to be 1. And then I'm going over. The only trouble is it's directly above the C, so I'm not going over at all. And then I'm coming down, and the down is 3. So by looking at this from a vector perspective, to find the angle B up in that corner, I just have to use the formula that we have with these vectors I've chosen. So once again, the cosine of theta is going to be the dot product, which is 2 plus 0 plus 9. And then the magnitude here, that's going to be 16, 25, is that 29, I hope? And this is going to be 10. So we get 11 over the square root of 290. We now take the inverse cosine or the arc cosine, and we have the angle. Again, I don't have my calculator up here handy, so I'll let you verify that. But this is one way we can use this thing called the scalar product. There will be others, but for now its main use is to find angles between vectors, or deciding if two vectors or two lines are actually perpendicular. You could also go with the idea of parallel, but of course parallel, the angle between them would either be 0 or 180, or 0 or pi, and then we'd have to just adjust accordingly. So we have the scalar product. When you look at section 9e, most of the problems have something to do with finding angles or manipulating the properties or the definition in order to get the properties. So good luck with the problem set from 9e. Later this week I will produce a video on some of the newer stuff involving vectors. But until then, if you have any questions, let me know, and have a good day.